Today we're going to talk about the heat of fusion and the heat of vaporization for substances. Specifically, what we're going to be focusing on today is water. So we have been talking about Q, right? And we've been talking about Q in terms of Q equals mc delta T, right? That the heat absorbed or released equals the mass times the specific heat times the change in temperature. Well, we know that on a heating curve or a cooling curve, that temperature changes only occur during these portions of our heating or cooling curves. But what if we need to calculate the Q for these sections here, where there is no temperature change? So that's where this heat of fusion and heat of vaporization comes in. We can actually look at a system, look at something that is going to be melting or boiling or evaporating or condensing or freezing, and look at that substances in multiple stages using heat of fusion and heat of vaporization. So the first one, heat of fusion, is the quantity of heat required to melt or freeze 1 gram of a substance. So this is fusion is to melt or freeze. So it is dealing with the liquids and the solid portion. So this plateau right here. The symbol that we use for heat of fusion is HF. And the unit that we're going to use for heat of fusion is joules per gram. And the equation is Q equals HF, heat of fusion, times the mass of that substance. Heat of vaporization is the second plateau in a heating curve, or the first plateau in a cooling curve. And it is the quantity of heat required to boil or condense 1 gram of a substance. And the symbol we're going to use for heat of vaporization is HV. The unit is the same as heat of fusion, which is joules per gram. And the equation is also very similar to heat of fusion, except it's now Q equals HV times the mass of the substance. So let's take a look at this little example problem right here. It says, how much heat is required to melt 25 grams of ice? Well, we're typically going to be given both of these values for water. So the heat of fusion for water is 334 joules per gram. And the heat of vaporization is 2,260 joules per gram. So this is HF, this is HV. So if we want to know how much heat is required to melt 25 grams of ice, how much heat is also known as Q, and we have a mass of 25, and we're dealing with ice, are we going to be dealing with heat of fusion or heat of vaporization? Well, since this is ice, and we want to figure out melting, right? How much heat is required for melting? We're going to use the heat of fusion. So we would use Q equals HF times M. So that means Q equals HF, which for water is 334 joules per gram, times the mass, which is 25 grams. And what ends up happening, since grams here is the denominator and grams here is technically in the numerator, those are going to cancel. So all we have to do is multiply 334 times 25. So we get Q equals 8,400 joules. And that is, I would calculate that. Okay, so now we have three, technically two, they're the same one, but three different possible equations to help us calculate Q. Well, how do we know which equation we're going to use? Q equals mc delta T or Q equals HM? So to determine which equation to use, we're going to sketch a heating or a cooling curve. So for this example, I have a heating curve. And what we're going to do is we need to figure out at what point of this heating curve are these situations occurring. Well, we know that solids exist here, solids and liquids exist here, so this is where something freezes or melts. Liquids exist here, temperature change, right? Temperature change. liquids and gases exist here, and then gases exist here. So let's take a look at this example problem, and we'll use the heating curve to help us figure out what we're going to do where. So this statement says, if a sample of ice at negative 10 degrees Celsius is placed onto a hot plate and becomes a sample of water at 45 degrees Celsius, how much energy was absorbed by the ice? So first thing we need to do is sketch a heating curve to map your progress through this question. So we have a sample of ice at negative 10 degrees Celsius. Well, if this is a heating curve and this is specifically for water, what temperature is this plateau at? This is where solid ice starts to become liquid. What temperature is this? Well, if we're dealing with Celsius, this is about 0 degrees Celsius. And then once all of the solid is gone and liquid starts to heat up, at what temperature does it start to boil? Well, if we're talking about Celsius, water starts to boil at about 100 degrees Celsius. So in this situation here, we have a sample of ice at negative 10, which means we have solid at negative 10, which is below 0. So we'll say that it starts around here. So this is the first section, right? Sample of ice at negative 10 is going to melt. It's going to melt. So we're going to call this section Section A. And then it becomes a sample of water at 45 degrees Celsius. How much energy was absorbed? Okay, well, we know that this section right here, this is where solid and liquid are coexisting. That is still at 0. So at what point would I mark 45? Well, 45 is going to be somewhere around the middle, right? So this is where the end of the situation occurs. Well, we already kind of talked about that we use this equation during times of temperature change, and we're going to use these equations at times of phase changes where there's no temperature change. So what I need to do is I know that I have this section A, which I'm going to use Q equals MC delta T because there's a temperature change here. This is going to be my second section. This is going to be section B, which is where there's a phase change occurring, where something is melting. So heat of fusion comes into play. And then my last section, where my liquid warms up to 45 degrees Celsius, is going to be section C. So what I'll do over here is I'm going to set up those 3 sections as 3 different calculations. Well, A, we have a temperature change. So if we have a temperature change, we're going to use Q equals MC delta T, temperature change. And then I'm going to use the information that I have here to figure out, okay, from this negative 10 up to 0, right? Negative 10 up to 0, let's figure out the heat. So if we have Q equals the mass, and the mass here, oh, I forgot to give mass in the example problem, sorry. So the mass is going to be, the mass of the sample is going to be 20 grams. Normally you'll be given the mass, sorry for this example, there isn't one, I don't know why I left that out. So let's say the mass for this example is 20. And since we're dealing with ice, what is the specific heat for ice? The specific heat for ice is 2.11. And then our temperature change. So for this section right here, from here up to 0, what is the temperature change? Well, our final temperature is 0 minus our initial temperature, which is negative 10 degrees Celsius. So when I multiply 20 times 2.11 times 10, I get Q equals 422 joules. So for this section right here, this section of A, I have Q equals 422 joules. All right, now let's calculate how much heat there's going to be for this section where there is no temperature change. This is where I'm going to use my Q equals HF times M equation, the heat of fusion, because this is a phase change. This is where something is melting. So if our mass is 20, Q equals the mass, right, times HF. Well, HF is heat of fusion, which we're given right up here. And I believe it might be on the backside of your periodic table. And if it's not, you'll be given that value. So 334 joules per gram times the mass of 20 grams. Right? These cancel. So our Q equals 6,680 joules for this section right here, this phase change. And then last but not least, we have one more temperature change. So it goes from 0, right? Our heat of fusion, it's melting from 0, and then it warms up to 45. So we have to calculate Q for that section. So again, we would use Q equals mc delta T. Q equals the mass, which is 20. Now our specific heat for this, since now it's already at C, it's a liquid, our specific heat becomes 4.18. Our final temperature is 45. The initial temperature for this section is 0, right? If we were looking at the whole system, it would be -10, but we already calculated that part, the 0 to -10. So now we're just looking at from 0, so this temperature is 0 right here for water, up to 45. That's why I included that part right here. So Q equals 3,760 joules. Okay, so now I calculated Q for these 3 sections. From here, this point of where it started, to this point of where it ended. So now what do you think I have to do with each of these Qs? Well, now this is the easy part. All I need to do is add them up. So 422 plus 6,680 plus 3,760. I get Q equals 10,862 total joules. And that is my final answer on how to solve for the energy that was absorbed by the ice from beginning to end.